I've been, obviously British, Manchester based for many years, but I've also spent a lot of time living in Colorado for 25 years now. And before that I was at the University of Colorado, Boulder, and the University of California, Berkeley, and Princeton. I've had associations with all these places, and just a little bit of background here. You may notice that these kind of mascots are all rather fierce-looking animals, and it gave me some hesitation when I was offered the job at the Colorado School of Mines, which had a donkey, or they call it a burro, but it's yet to be explained to me why it has dynamite stick in its mouth. I hate to think it was some sort of sacrificial animal going down the tunnel, but I think that was canaries, perhaps. Talking of logos in the United States, this is one of my favorites actually. This one is real, University of California at Santa Cruz. I was at the University of California up the road in Berkeley. The students overrode the administration who wanted a lion or bear or something, and voted the banana slug as their university mascot. Colorado School of Mines, obviously in Colorado, just east of the Rockies, if you've ever been out that way. The very sudden rise in elevation just here. Everybody lives just to the east of the Rockies. It's quite close to Denver. It's the big regional city there. So UK and Ireland. I was born in London. I spent a lot of time in Manchester, and I'm on sabbatical right now, spending the second half of my time in Oxford. As for the rest, I'm still trying to figure out. I'm going to be here at a pretty critical time. How much longer? 3 weeks to see what happens. Certainly flying here, they wouldn't let me buy any vodka because they said it's EU to EU, so maybe something might get better later on. Let me give you a brief outline of my talk, which is called Risk Assessment in Geotechnical Engineering. Very general discussion today, no hard sums or anything. It's going to be just a review of some of the benefits that risk assessment offers, especially in geotechnical engineering, and there's some structural people here, and some of the methods that we can use to actually perform a risk assessment study. I'd like to start talking about slope stability just because it's such a widely used application in geotechnical engineering. And I'd like to talk a little bit about the use of the finite element method to find the factor of safety of the slope. It's one of the options we have in our toolbox for finding the stability of slopes. And with a special emphasis on the variability of soils, which I suppose makes our engineering material that we have to deal with uniquely tricky because the properties can vary so much. And then I'll move on to a review of risk assessment methods in the geotechnical world. I'll probably define what I mean by risk before I start off on this stuff. But I'll identify what I consider 3 levels of probabilistic analysis, ranging from fairly simple non-mathematical methods through to something you can do on a laptop and relatively quickly to heavy-duty supercomputer stuff. So we won't be talking too much about that. Then I'll conclude with a few remarks at the end. Juan Pablo mentioned that I spent time as a director of the ASCE, which is the American Society of Civil Engineers, of course, and it's getting closer all the time, this target date of 2025, but this document, which was when it was delivered when I was on the board of the society, they came up with what they thought would be priorities for civil engineers in the year 2025. Maybe this thing was done about 5 years ago now. Most of it I found a little bit bland, perhaps a little bit lacking in detail, but one of them caught my eye, and I really liked the fact that they recognised that in the future engineers and civil engineers, all engineers will have to perhaps consider and manage risk. Not only assess risk, but manage it and deal with it in a scientific way. Leaders in public policy, well, yeah, we would like more politicians to be engineers, not lawyers, certainly where I live nowadays. The motivation for a probabilistic risk type, did something jump? Oh, this screen is sort of slightly differently adjusted, I think, with the projector. Actually, I dropped off the Geotechnical panel as of the 1st of January this year, but the very first volume of Geotechnical, volume 1, number 1, they asked someone called Carl Terzaghi to write a preface to the very first volume, and he pointed out what we all know, I suppose, but don't often confront explicitly the fact that engineers have to deal with soil and rock, where properties are varying from point to point. The engineering properties are not uniform, and often we only sample the properties in a few limited places. The same year, many of you will know of a quite important book by Donald Taylor, that same year, from 48, I don't know if it's a coincidence, but in his introduction he talks also about this variability that we have to deal with in the geotechnical world. I think there was quite a lot of rivalry in those days. It's a small world of geotechnical engineers in the academic business. Donald Taylor never got promoted, even though he has more things named after him, almost as many as Terzaghi, I would say. You've probably heard of his consolidation methods and his slope stability charts. So it's a pretty tough political world, I think, in those days. However, in spite of Taylor and Terzaghi's pronouncements, only fairly recently, in the research world at least, have started to confront these variabilities explicitly through numerical methods. And I'm not going to dwell too much on this, but this is a method called the random finite element method, where we model the soil or rock using a finite element mesh, and the properties are defined statistically with a mean and a standard deviation. If you remember a bit of your probability and statistics, instead of giving the whole problem a single property, which is traditional geotechnical engineering, we slap a factor of safety on at the end, we'll actually try to explicitly predict or model the soil as a variable material. This is a bearing capacity analysis, which we did some time ago. You can see a sort of grey, dark scale that somehow represents the strength. I think dark represents weak in this picture, and light represents strong soil. It's sort of interesting to see the mechanism goes one way. When we do these things repetitively, that's sometimes called Monte-Carlo simulations, we very rarely get a bearing capacity failure that does the classical textbook, symmetric thing. Just never happens, because a weak point somewhere triggers the failure to go one way or the other. I've thrown in a celebrated bearing capacity failure in Canada from a few years ago, 106 years ago actually. This, of course, as we can see, it went one way. Slope stability analysis by finite elements. I want to emphasize perhaps the power of the finite element method here for dealing with this variability that we all know is there. Suppose we want to calculate the factor of safety of a slope. Well, we can use limit equilibriums, methods of slices, or we can use charts, sometimes Taylor's charts for certain simple problems, or we can use numerical methods like the finite element method. This is how it works. It's very simple and very powerful. You design your mesh to represent the profile of the slope. It could be a lot more complicated than this, but I've got a simple slope. We turn on gravity, so we slap on, after all, it's gravity that's driving the failure, if there is one. And then we give the slope, the soil, a rather simple stress-strain law. Something elastic, perfectly plastic, this would be called. We assume the soil is elastic for a while, and then when it hits a threshold defined by Coulomb, friction, cohesion, it fails. So the way this works is we do initially an elastic analysis. We just forget Coulomb, we just do an elastic analysis with Young's modulus and Poisson's ratio. And we look at the stress in each element, one at a time, to decide if the stresses in the element generated by gravity have violated Coulomb. If they're up above this line, they're strayed into illegal territory. If the stresses are below the line, we consider them still to be elastic. So we're not worried about these ones below. We have a little parameter called m. If m is positive, we're happy. If m is negative something, I think I might have got m the wrong way around here. If m is, I think we now have m is positive, it's bad, m is negative, it's good. Should the misprint there? Maybe not. So this is what happens. If a particular element violates Coulomb, negative in this case, then something has to happen. Stresses are not allowed to be in that part of the chart. They've exceeded their strength that is available. So we then turn on a little redistribution algorithm that tries to share the excess stresses with neighbouring elements. So these are finite elements, each of these little quadrilaterals, and there's a fairly simple bit of programming that says, okay, let's try and get our neighbours to take some of this load. In doing so, we may cause the neighbours to fail, in which case they will need another round of redistribution. So it's a redistribution algorithm that we're doing. We're moving the stresses around, but we're not violating equilibrium. And we must still be in equilibrium with gravity, but we're moving the stresses. And after a while, hopefully, all the elements have returned back to Coulomb's line within tolerances, and we stop calculating. To find the factor of safety, we keep gravity constant, of course, unless we're going to Mars or something. Keep gravity constant, and we gradually weaken the soil by dividing by something called a strength reduction factor, SRF. So we systematically weaken the soil, and sooner or later, the slope's going to fail. Obviously, if you weaken it enough, it will fail. And when that happens, it's easily shown, I'm not proving it today, but it's easily shown that the strength reduction factor is the factor of safety. And what we see in our model is a very sudden increase in crest movement, sudden increase in nodal displacements. So the strength reduction factor is increased slowly, and suddenly we get this failure. That's the factor of safety. And we validated it against old, for simple problems, we could check the answers against established results in the literature and elsewhere. So if we're just solving problems that we can get out of a book, that's not, what's the point? So when you start doing different and more difficult problems, that's when it starts to come into its own, I think, this method. This is a layered soil with a kind of celebrated benchmark problem that many people have looked at called the James Bay Dike. Never got built as far as I know, but it was a lot of discussion about it. The finite element approach seeks out the critical failure mechanism. You don't have to tell it where to look. I didn't have to, in advance, say look for circles going through the toe or tangents of this depth or anything like that. So the mechanism comes out of the analysis naturally. And in a sense, it's a numerical virtual world of computer modelling. It's somehow more natural that the mechanism seeks out the weakest path through the soil. In this case, obviously, there's a weak layer at the bottom somewhere, and it's attracted. There's a very translational sort of failure down here. Eventually, it has to outcrop at the beginning and the end. And a few other examples that this is a bit more contrived. This is like a two-layer problem with strength reduction. So we're now reducing the strength of both of these layers at the same time until something fails. If we increase the strength of the lower soil a little bit, and obviously I've chosen my numbers carefully to give this answer, but you can see we have two mechanisms with the same factor of safety. So the shallow one and a deep one, both with the same factor of about 1.14. If I increase the strength of the lower soil once more, then essentially the mechanism no longer wants to go deep. It's harder work to get through that lower, stronger material, and it stays shallow. I think my point here is the finite element analysis, and by the way, it's a program downloadable you can all have if you're interested. It does this. Is it naturally gives you those mechanisms. I didn't have to tell it to look for them. Just when I finished the run, I looked at the graphics. We see. And I do ask the question here that would a limit equilibrium method have found both those mechanisms necessarily? I think maybe in the hands of a very experienced practitioner, but I think most conventional slope stability analysis would have found one of them and said, hey, that's it, we've got the factor of safety, without realizing there's another equally likely mechanism of failure lying underneath. When you get back into this random world of soil properties, which is much more variable than our little simple layered problems, we really have no choice but to go to numerical methods because the mechanisms can be quite wild sometimes as they seek out a path through the weak soil. Okay, so that's a little bit of background on slope stability by finite elements. Now, why would risk assessment, what does it add to the conventional approach? Well, here's the conventional approach to the slope stability analysis again. Two slopes, both have the same factor of safety. I think you'll see exactly what I'm getting at here. Both slopes have failed, both have a factor of safety of 1, but one is obviously much more damaging, potentially hazardous to the people living downhill, which raises the issue of consequences of failure. Clearly, the consequences of the right-hand event are much more serious in terms of cost, lives, potential loss of life, and so on. So here's my definition of risk, a very simple one. It's essentially, risk is the probability of failure weighted by the consequences of failure. So, if the consequences are serious or very severe, then we can tolerate, we can only tolerate a much lower probability of failure. If the consequences are not so severe, we can tolerate a higher probability of failure. It makes perfect sense. The thing is, the probability of failure of anything is rarely equal to 0, and we always have to recognize that failure is possible, and we have to manage that level that we could accept based on consequences. And consequences are going to be very site-specific. I can't just put in a textbook somewhere, an acceptable probability of failure for a slope or a retaining wall or a foundation. It depends on what the consequences would be if that thing failed. What is acceptable risk? This is a topic that I daren't touch on today, and I think it's a very difficult one to tackle. It's a different lecture entirely. Acceptable risk is something that perhaps society will have to buy into. How much are we willing to pay to reduce risk? What can we live with? Just to give you an idea of how this sort of pans out, this idea of risk. This is a historic graph. I hope you can just about make it out. Becker, in 1982, he claims he developed this chart based on earlier work that was unpublished by other people. He doesn't want to take full credit for it, but it's one of the earliest publications of this type. Along the x-axis is, in this case, dollars, cost of repair, infrastructure damage, and so on. And of course, it's 1982 dollars. Up here is an acceptable level of probability of failure. So the y-axis is probability of failure, the x-axis is lives lost, and these not lives lost, dollars cost, the top axis actually is lives lost, which raises another interesting controversial issue of how much is a life worth. I didn't plan to get into this one. But if you Google it, you'll find a huge bibliography on this topic. I suppose when I mentioned it, the lies lost goes into logarithmic scale, you've got a tenth of the lies lost here, so I wonder what that is. So, it's broken arms. But, so these black lines are Becker's chart somehow define the sort of cut-off between what might be unacceptable and what might be acceptable for design. Unacceptable is high cost of repair and high probability of failure. Those two obviously don't go together. If the cost or lives lost potentially is very high, you've got to target a much lower probability of failure. Now this graph has appeared in many different forms of different agencies, but they all have a similar idea of diagonal lines going from the top left to the bottom right. So a risk assessment study involves probability and consequences. I'm going to talk more about probability today for the rest of this lecture because the consequences are going to be much more site specific. How do we estimate probability of failure? The probability of failure is somehow an alternative to the factor of safety. I think right now it's more of a complement. Nobody's going to abandon the old ways of doing things because they've served us well and generally safely. But the probability of failure, I think, is a more scientific way of thinking. The factor of safety is just an abstract number that doesn't mean 1.3. What doesn't mean a great deal other than it's higher than 1, and you feel good about that. But actually the terminology in the literature, in my experience, is quite variable. Some people would prefer to not talk about failure if it's not going to be, if it's the probability of differential settlement under a building or something that's not terribly high consequences. We might talk about the probability of inadequate performance or the probability of design failure. And some more optimistic people prefer a more glasses half full a way of thinking, reliability or the reliability index. Mathematically, these are uniquely related. So if you know the probability of failure, you know the reliability. So some investigators, some users prefer to talk about reliability. It feels a bit more positive. So what, if any, is the relationship between the probability of failure and the factor of safety? This is, I'll show you in a minute, but this is a dangerous world to get into trying to compare these things. But I've got two slopes, and this is a very famous example actually, you may have seen it before elsewhere. I took a simple slope and I analysed it twice. The only difference between example 1 and example 2 is that the friction angle is higher in example 2. Cohesion is dimensionless in this case, but the cohesion is constant, the geometry is constant, friction is high. And not surprisingly, you don't need finite elements for this one. You can look up in charts, take your pick, there's lots of choice out there. The second one, not surprisingly, gives a higher factor of safety. No one is going to be remotely surprised to hear that. And so, in conventional thinking, slope 2 is safer. You probably already guessed this is a trick question. Right, let's say someone goes off and, hey, wait a minute, this soil in this slope is not constant, does not have a constant friction angle, it does not have a constant cohesion, it's variable. And they do some analysis, a probabilistic analysis, which I'll mention briefly later. But let's say following a probabilistic analysis, we come up with some more information about the variability of the soil properties. And some analysis has shown, for example, that example 1 has a mean factor of safety of 1.5 and a standard deviation of factor of safety of 1.18. I'm guessing you remember enough about your probability statistics that the standard deviation is a measure of the spread of results. how dispersed they are. So really what this is saying, that the mean factor of safety is indeed what we calculated using charts just before. Example 2 gives a mean factor of safety of 2 and a standard deviation factor of safety rather higher, significantly more spread out. Okay, so how do we interpret these findings? We can plot them as so-called probability density functions. Normal, I'm assuming they're nice normal distributions or Gaussian distributions, perfectly symmetrical, bell-shaped curve. And here are the two results. This is example 1 with a mean factor of safety. This axis here is the factor of safety. This axis is somehow the likelihood of each value of that factor of safety. And here's example 2, which is flatter and more sort of squashed out. If these things are drawn properly, by the way, and this is quite important, if these curves are drawn properly, the area enclosed underneath them is equal to 1 unit of area. And this makes it rather convenient to calculate probabilities as areas. So the probability, for example, of the factor of safety being less than 1, which means failure, is the area of these curves to the left of the factor of safety of 1. You can probably see what's coming. If I just look at a detail of that corner there, we can see that the blue line, which has the lower factor of safety, has a smaller area, which means a smaller probability of failure, than the so-called safer slope, which is more flattened, has a higher probability of failure. So we get this counterintuitive result that's sort of a bit unsettling in many ways. The safer slope has a higher probability of failure. Now, this is a contrived example deliberately to make a point here. And the point is that direct comparison between the factor of safety and the probability of failure should be done with great care. And in fact, they're apples and oranges, actually. A factor of safety is a single number. A single number. Factor of safety is 1.5. A probability of failure depends on at least 2 numbers, a mean and a standard deviation. So, I regularly see people writing papers where they're comparing probability of failure and factor of safety. And one has to say, well, you need to have a lot of small print caveats here to explain under what circumstances you're doing that. How do we calculate this factor of safety? How do we calculate this probability of failure? Let's just recap using that bearing capacity problem. Classical soil mechanics undergraduate problem, right? So we have the traditional approach, that's just about visible at the top here, is we have a footing with soil with certain friction and cohesion, which has been chosen conservatively in some way, some characteristic values. We plug them into a formula like Terzaghi. We calculate the bearing capacity. We look up the bearing capacity factors and we get the calculator out and we work out Q volt. And then what we do, we divide by 3 or something like that, and which is a typical factor of safety for a bearing capacity problem. And we end up with an allowable value which would be given to structural engineers perhaps. Say, okay, you can safely apply this pressure to our footing. That's the traditional approach. The probabilistic approach inevitably involves more information. That's where we're going to start saying where we're going to get it from. Someone will ask them for it in the end. But now, we're not going to reinvent soil mechanics. We're still going to use Terzaghi. We don't want to change the models that we've been using. That's not now anyway. But now we might need means and standard deviations in the book. We want to know how variable these properties are coming into the formula. And in here we have a probabilistic method. We'll mention briefly 1 or 2 ways of doing that. But instead of calculating the bearing capacity, like we did in the previous slide, we're now going to, oh, there's a couple of other things here, but we're now going to calculate the mean and the standard deviation of the bearing capacity. So, probabilistic stuff coming in, probabilistic stuff coming out. And these blue comments are somewhat, if you want a somewhat more sophisticated analysis. For example, cross-correlation says that these variables coming in may not be entirely independent of one another. They may be correlated in some way. But a spatial correlation recognizes that soil properties, if you take two samples in a field that are close together, physically in the field, they're more likely to give you similar properties than if you take all holes in opposite corners of the field. So the stratification, the depositional history tends to give you a spatial effect. But these would be reserved for a more advanced analysis. What do we do with these things? I mean, we somehow filtered these variable input to give a variable output. Well, now you go to probability tables or something in the back of a textbook, or you get your calculator out, and we can then, given this variability of the bearing capacity, we can calculate the area, if you like, to the left of some critical minimum value that would be acceptable for design. Here I've written it as what's the probability of failure? We've lost a little bit at the bottom here. The probability of failure, for example, what is the probability of failure that the bearing capacity is less than the allowable value that we obtained from our factor of safety approach? That would be bad, right? If the bearing capacity, in fact, was less than Q allowable. No doubt it's not zero, it's a small number, hopefully. I shouldn't say probably. In this kind of lecture, my colleague Gordon Fenton was ticking me off for doing that. So here's the key thing for any probabilistic analysis, I think. How does variability of input affect variability of output? Where do these means and standard deviations that we come from? That's a good question, because geotechnical engineers are always complaining we don't have good enough site investigation, right? Today, how on earth are we going to get standard deviations? Well, of course, there's no substitute for a good far-out site investigation where you have enough data to actually calculate a standard deviation. But in the absence of high-quality data, we would initially recommend resorting to what we might call typical values of variability in different soil properties. There's a growing bibliography of this. If anyone's interested, I have a list of papers and books and things that just give you a ballpark feel for how variable different properties are. This is actually a very good, very pioneering work from Australia, actually, this book called Lee, White and Ingalls. But there are more recent ones, long lists of properties and typical ranges of variability. I'm going to talk about 3 levels. One, called an expert panel. This is where a group of experienced engineers and scientists who are related to the project will sit around the table and construct something called an event tree. I'll show you a very simple one in a minute. An event tree involves really these experts trying to assess what they think the probability is of various things going wrong in a design. So it's a little bit, it sounds subjective, but actually it's based on many years of experience. These people should be seasoned engineers with lots of training in their discipline. A powerful and very simple method that involves a little bit more calculation. The first one involves no mathematics at all, really, based on experience. And by the way, this is the one that's in state of practice, largely. Just down the road in Golden, Colorado, there's the US Bureau of Reclamation, which you've probably heard of. They're responsible for hundreds of earth dams, mainly west of the Mississippi. Corps of Engineers have tended to be more east of the Mississippi. but they're regularly doing the entry calculations on existing dams that have been re-evaluated for liquefaction risk and things like that. First order methods are becoming fairly routine. This involves a laptop or a calculation that can take a few seconds, but involves some calculation and delivers the probability of failure of the design. FORM. And the third one is Monte-Carlo family of methods where you just crank the handle over and over again with variable input. You keep on calculating until the thing that you're interested in calculating, the output quantity, starts to settle down statistically. You've done it enough times that your output is starting to stabilize. I'm just scratching the surface a little bit, but this is a simple Monte-Carlo. I'll show you a quick example of that. And then this so-called random finite element method I mentioned right at the beginning is also not in this camp, but involves a bit more computational effort. So expert panel. This is one I pinched from the Bureau of Reclamation in Colorado, but I edited it a bit to, take out a few names and things. But this was actually a re-evaluation. I'm sorry, the writing's a bit small. This was a re-evaluation of an old dam, 100, well, not maybe 80 years old in the northwest, and they were worried about a liquefiable layer existing under this embankment, and the danger of an earthquake coming along and causing liquefaction. So the panel sat down and tried to thrash out the things that might happen, and the things that might go wrong. So just to give you a quick flavour of this, the starting point, the red blobs are bad things happening. If all the red blobs join up, then you're in trouble. The first question they ask is, based on some limited site data, no doubt, what is the probability that the layer of liquefiable material is continuous from upstream to downstream? And based on the data that they had and their experience, they decided there was a 70% chance that yes, it was a liquefiable layer that potentially existed underneath this thing. No, 30%. This is called a tree because you've got branches coming off branches. And one golden rule of entry, I'm sure some of you have experience of this, is that the probabilities on all the branches must add up to 1 or 100% in this case. So you must cover all the bases and make sure you've got every. And if the questions are reasonably simple, to be a yes or a no. Second question they considered is what's the probability that the reservoir is full, or at least very full, very high at the time of some earthquake. This would be more of a based on data, I suppose, over the years, but they decided that the probability of the reservoir being above a certain stage was about 30%. And so it goes on. Here's the red, bad thing happening. Then they looked at the various ranges of earthquakes that might occur based on magnitude and distance from the site. And the most likely one that they thought was going to affect this particular embankment was this one. And the probability is really coming down. An earthquake in Washington State, which gets earthquakes, but it wasn't particularly active area. And then, so these are the circles. Then they said, well, will that layer liquefy? Maybe it won't liquefy just because there's an earthquake. And finally, here is my truncated version. If everything bad happens at the same time, then what's the probability that the crest will deform more than the freeboard of the reservoir, which would result in a release of water? So that was considered to be 5%. So this actually was a much longer thing that I cut down. At the end of it all, assuming all these events are independent of each other, which is a sort of statistical term, but if they're all independent, then the probability of failure of overtopping is just the product of all those numbers circled in red. Just multiply them all together. You shouldn't really use percentages, it's better to use absolute numbers. So I'm not using percentages up here. But yeah, in this case the number was very small, and I think this would have been quite acceptable to them at the time. By the way, I don't really take much credence in these numbers here. Nobody can possibly nail it down. But you know, that's the most important number. If some design changes that number to -6 or -8, then we're already onto something. So the volumetry is very much used in practice to estimate probabilities. Second, first order reliability, and I realise we've run a little short time, so I'll push on. First order reliability method is based on, I've used Excel on my laptop. Again, the programs are downloadable if you want to play with them. This is the bearing capacity problem. Without going into some of these stuff, I'm saying that the Q allowable for this footing must be 300. You should not apply a load of more than 300 kilopascals in this case. Q allowable. However, the properties here are variable. Unit weight I'm not going to deal with. That's pretty constant compared to some of these other properties. So cohesion and friction are going to be treated as random variables with means and standard deviation. Distribution types, well, with lots of choice here, but we'll stick with normal, the nice symmetry. So, I've also thrown in some cross-correlation just for fun, but some people think that the friction angle and the cohesion are negatively correlated. That's controversial. That is to say, when the mean is high, when the mean of the friction angle is high, the mean of the cohesion tends to be low, and vice versa. Maybe some data has suggested that. So our main question today here is, what is the probability of the bearing capacity of this footing being less than 300? You know, if we're unlucky enough to happen to have weak soil that happens to lie underneath this footing, that would have to happen. By the way, a conventional Terzaghi calculation based on the mean values would imply, in this case, a factor of safety of 3.6. Just plugging these into Terzaghi's bearing capacity equation and dividing by 300. So this is the first order reliability method. This is how it works. Previously we had a nice normal curve that just was on a piece of flat paper. Now with two random variables, namely the cohesion and the friction at the same time, you get a hill. So it's the kind of three-dimensional version of a normal distribution. The top of the hill is the most likely value of the cohesion and the most likely value of the friction angle. As you move down to the tails, yeah, okay, you might get a cohesion with a very small number, but it's sort of unlikely you get out into the tails of this hill. Consider all the combinations of C and tan of phi that might result in failure, that might cause the factor of safety to equal 1. There's actually an infinite number of them. Some of them are incredibly unlikely out in the tails here of this hill. But you know, you could have a huge number of possibilities that might cause failure. For example, the cohesion might be very small, or the friction angle might be very small. You know, critical place under the footing. So this line, which is a bit of I think of it like a wall cutting through the hill. The volume, instead of areas now, we have volumes. The volume of the hill on the failure side is the probability of the factor of safety being less than 1. The volume of the hill on the safe side is the probability of not failing. Now what the form method does, this first order reliability method, is it finds the most likely combination of C and tan of phi to cause failure. That is the values that are nearest to the top of the hill. That's the first order reliability method. The most likely failure point. Okay. It could fail down here, but it's incredibly unlikely because it's a long way into the tail. So this is actually an optimization method. It uses Excel, or I don't know what, if you like to use MATLAB or one of those. But Excel is, most people have it if they have Word. Looking down now on top of the picture, here's the top of the hill. This was the red line of failure, corresponding to the factor of safety equaling 1. Failure on this side, not failure on that side. Form, F-O-R-M, first order reliability method, will deliver this point here with the lowest contour. You think of these contours getting bigger as you move away from the top of the hill. You will find the point with the smallest contour value, the least reliable result. These contours are of reliability index, actually. So the smaller that number, the less reliable your design, the higher the probability of failure. Just for the record, it's called first order reliability method because, strictly speaking, once it's found that point, it replaces the actual failure line by a straight line approximation. That's hence the first order. It looks, I've exaggerated it here just to show the two different lines are not the same, but in my experience, and I've asked around quite a bit, very often this first order approximation is very good, very close to the original. We've got some do-it-yourself Excel spreadsheets. I don't need you to look into this, squint too hard at this, but yeah, they're all downloadable if you like. If any of you are familiar with the solver add-in on Excel, if you have Excel, you've got the add-in potentially. It's an optimization, Excel's optimization program, because it's called an optimization because we're trying to find, by iterating values of C and tan phi, it finds that critical value that's closest to the top of the hill. The yellow numbers are user inputs, so some things I'm not going to treat as random variables. These the width of the footing, the depth, and so on, I'm treating as constants. These are the random variables, mean and standard deviation. You can change these and play with it. It's very interesting just to see how it affects the results. And here, if we have cross correlation, you can put it in. If you want, this number can lie anywhere between -1, which would be perfect negative correlation, or +1, which would be perfect positive. More likely, we'll just put 0 here because we don't have enough information to know if the correlation is significant or not. If we do this data solve thing on Excel, you'll get a probability of failure. This will take a split second to run. What this is saying is that the probability of the bearing capacity falling below 300 is 0.21%, which corresponds to a reliability index of 2.86. Just level 3, Monte-Carlo, is the last group of methods. Monte-Carlo is a very simple idea, but can be a bit more computation intensive. You repetitively do a calculation, and each time you repeat the calculation, you use different random values of C and tan phi. So this is actually exactly the same problem I just solved using first order reliability method. Exactly the same problem, but now cranking the handle with Monte-Carlo. Again using Excel. So now what I need to do is generate random values of C and random values of tan phi that are based on this underlying distribution with a mean of 4 and standard deviation of 1. And then for the friction angle, the random input is this mean and standard deviation. So don't worry too much about how I did it. If you're into Excel, you might look at this more closely. But essentially, in this example, I'm generating 100,000 repetitions, which is probably overkill. But the more the merrier in Monte-Carlo. And if computer time is an issue, then we might have to cut back on this. But here's a very nice check that Excel is generating random variables. at the very end of your 100,000, calculate the mean and standard deviation. They should be equal to what you used to generate them. And if they're not, then something is wrong. These random number generators have improved enormously over the years, and now they seem to check out very well. So this is just a check. The cross correlation is about 0.3. So now what do? We take these C's and tan phi's and we stick them into Terzaghi's bearing capacity formula. So we just do Terzaghi over and over again. A conventional calculation of Terzaghi. Let's not worry about that line too much. Oh no, we will. This is good. Okay, here's the C and tan phi that I just took from the previous slide. Here's all the correction factors and bearing capacity factors in ancient Terzaghi. I'm getting 100,000 different bearing capacities. Every one is different. And the ones I'm interested in are the ones where it's less than 300. So if it's less than 300, I'll put a little 1 in that column. And at the end of it all, well, you can see nearly everything is 0, but we add up all the ones, and we get 212 failures out of 100,000. I've left out quite a few here, you can see. We wouldn't want to look at all those, would we? So we add up all the ones and simply divide by 100,000. Couldn't really be simpler. You count how many times some event has occurred, and you divide by the number of times you repeat it. The probability of failure is 0.21%, which of course is exactly what we had before. I wouldn't have shown it to you otherwise. But in this case, what this is saying is that the Monte-Carlo is really confirming that the first order approximation was very good. We didn't really know that properly until we did the Monte-Carlo, actually. There's no assumptions here. We just hammer away. Each line is an ordinary Terzaghi calculation with constant properties. Just the constant properties are different from one simulation to the next. Now, each Monte-Carlo simulation is a regular Terzaghi bearing capacity calculation, but with C and tan phi different each time. This is the example I just did, actually. This solid line is the separation between safety and failure. So all these little dots, there are 212 dots presumably under the solid line. These are all the combinations of C and tan phi that led to a bearing capacity of less than 300. The vast majority, of course, are well. It's like a galaxy of points. It's 100,000 dots. If you change the correlation, you just get different elongations of the galaxy. If the correlation is 0, then you just get a sort of ellipse sitting on the x and y axis. Okay, very final few words about this random finite element method, which is more of a research tool, but is also finding its way into proprietary codes. Now there's 2 or 3 that include this. This is the ability to spray a finite element mesh with a statistical distribution of properties. It's quite old in a way. I developed it with my colleague Gordon Fenton. We ended up writing a book that describes it. It combines random field theory, which is a little mathematical for me, with finite element methods. It accounts for spatial effects, the tendency of properties to cluster spatially. You have strong zones and weak zones. We can control that clustering effect. It takes account of finite element size. It's a little bit obscure today. All the programs are downloadable from the website. Source code a lot. If you have the stomach for it, lots and lots of Fortran code there. Gordon Fenton, who works at Dalhousie University in Canada, there have been a lot of short courses for ASC and international, as one Pablo mentioned. And many groups are now using the method, and it's found its way into some proprietary codes. If you give it away, I suppose you can't complain if others use it and sell it. So we've applied this method to many different areas of geotechnical engineering. Conventional methods, settlement, where the Young's modulus is the random variable, the compressibility. Maybe so in accounts people prefer to talk about compressibility. The spatial correlation idea is this clustering properties, which can be anisotropic, by the way, because that's quite important in soil layering sometimes. We can have much stronger correlation horizontally than vertically. These cases are not. These are isotropic. Line hill stability, bearing capacity, we already saw that. Seepage, one of the earliest ones we did, where the permeability is now the random field. Get these wobbly flow nets as the seepage is attracted to the high permeability zones and wants to avoid the low permeability zones. Earth pressures, active and passive. You don't usually get a nice ranking, 45 minus 5 or 2. The random field tends to attract the mechanism to the weak soil. We've got PY programs that have naturally maximally loaded piles with random spring stiffnesses and pile analysis. Slope stability I've talked about enough. Here's two simulations from a set of Monte-Carlo analyses with exactly the same input parameters. But in this case, the weak soil happened to attract a very deep mechanism, and this one was a much more shallow, landslidey kind of thing. Animation of those just for fun. Both simulations have the same statistical properties. So some of these mechanisms can be quite different in a Monte Carlo context. All right, let's wrap up a few concluding remarks here. The natural variability of soil and rock makes it well suited to a statistical approach for properties, for defining the property. Instead of a characteristic value, that we perhaps do in a traditional approach, we will actually recognize the variability with a normal distribution. We often use log model, but that's another story. Numerical methods, like the finite element method, like the finite difference method, if you're a FLAC devotee, are really the most powerful methods for dealing with this variability. And in highly variable stability problems, these methods allow the mechanism to seek out the weakest path through the material. We don't get nice circular mechanisms necessarily. We talked a little bit about factor of safety and the probability of failure. We should not compare them in a cavalier way. We should recognize that these are quite different things. Factor of safety is one number, whereas the probability of failure involves at least two numbers. They're not directly comparable. Geotechnical engineers have a toolbox of methods for probabilistic analysis, and we've touched on event trees, first order methods, and Monte-Carlo. And when Monte-Carlo is starting to do with non-linear finite element analysis, the analyses can take days. So, we're into a different world then. But there are some very powerful, simple methods, I think, that get you started and enable you to do parametric studies that will at least get you into feeling how parameters affect the result. How sensitive is the output to input parameters. All the programs I've described today are downloadable from my home page. And I think these slides are going to be made available to you somewhere on a site somewhere, so give it a try. Contact me if you try it and get stuck. And there's Blast of the Burrow. That's it. Thank you very much.
Thank you very much, for giving a very intuitive guide through a very complex field for us, and using plain language to give pragmatic examples and potential examples. We're running on a little bit, but if we have time for maybe one or two questions, I don't know if there's any pressing questions. Not Ken.
Yeah. Thanks for a great lecture. Two quick questions. First of all, how many measurements of the friction angle? I know we used the shallow formation example. Yeah. This is a reference, but how many measurements of the friction angle would you need for statistically significant distribution?
Secondly,
which friction angle do you use?
Yeah. Which Next question.
You can ignore the second.
No, okay. This is critical state sorting, actually.
Yeah.
Gordon Fenton says you need at least 20,
Okay.
but you know, there's the more the merrier. If you have good data, there's an increasing bibliography of typical values, I mentioned that, and some fantastic databases. It tends to be site specific, so that's the slight point. 20 would be certainly a minimum. But as for which friction angle, well, you know, if you want to be super conservative, I suppose you'll use the critical state angle, or the constant volume, or the residual friction angle. You realise I went to Manchester, so I'm not a full, true believer that the need for good quality data is as strong, if not stronger, it was. There was quite a good quote from the ICE, I think, some years ago. I'm not sure who it was attributed to, but it says you pay for a site investigation whether you have one or not. Little John maybe, but like, needs checking. Good to see you, by the way. Not sure we met often.
Any more